Bismillahirrahmanirrahim. Greetings. This is going to be the fourth lecture in a series building toward the Fundamental Theorem of Calculus. Now, I was going to outline the topic of this lecture and indicate them verbally. But then I came to the idea that if I put them in writing and put them on the board and to do it, because initial learning is so important, so that you can have the chance, the opportunity to pause, then think and reflect and contemplate before you pass it and go to the next. So please pause and do not pass it until you fully have comprehended. Unfortunately, because of the technology of computer, you have that great opportunity. So why not to use it? Now, before I start, let me say a few words about the limit. The two examples that you are familiar with from high school, one of them is a geometric sequence, like 1, 1/2, 1/4, 1/8, 1/16, and so on and so forth, that converges, meaning has a limit, and the limit of that is 0. All right. Now, the corresponding series of this sequence, of this geometric sequence, is 1 plus 1/2 plus 1/4 plus 1/8, and so on and so forth. Again, this series converges. The limit of that is 2. Limit. Now, in this lecture, we are talking mostly about the limit. The process of getting to that limit, we have already talked about. I may also go over shortly, but the point is about the limit, the concept of limit, and process of that is related. It's not that they are not related, but we just talk about the limit part of it. Okay, then let me get started, shall I? May I? Okay, I have this one on board. Let me zoom it if I may. Okay. Let me stay out of the way. Now here, let me, by the way, cover that so that I go one by one at a time. Now, x comma f of x is a point on the original function. Let's call it mother function. X comma f of x is a point on the original function. And x comma f prime of x is a point on the derivative function. Do you find me? Notice that I'm using x for both of them. There is also a point for that. Now, next one, we know a slope, we have gone over that, but repetition is a good process of learning, especially for the beginners. A slope is rise over run. So therefore, a slope times run will be rise. So if I use a slope as a s, so s times r equals to large R that I use it as a standing for rise. Now, the limit, here you are. The limit of delta x as delta x approaches 0 is, we show it with dx. So dx represents the limit of delta x as delta x approaches 0. And as delta x approaches 0, then that makes the limit of delta y to be dy. So dy is the limit of delta y as delta x approaches 0. Do you follow me so far? Now, next one is about the tangent, the slope of tangent. Let me read them for you. A slope of tangent line at x comma f of x, which is a point on the mother graph, on the f of x, is a point is the limit. The slope of a tangent line at that point is a limit of the slopes of the corresponding secant lines. So it's the limit of the slopes of the corresponding secant lines. So please pause, look at them carefully, think, contemplate before I go to the next. Okay, now let me cover that one and go over that. I'm reading them again. The slope of tangent line to the graph of a differentiable function f of x at the point of tangency is the limit of the slopes of the corresponding secant lines converging to the point of tangency. I repeat that one. I have repeated that one from the previous. It's just going that one more time. You follow that? Now, look at this one. The instantaneous rate of change of f of x, mother function, is, and the rate of the change of the tangent line at the point of tangency are the same. Now, this one is repetition of the same thing. As I said, repetition is very important, and that is very important concept, so I repeat that twice. So at the point of the tangency, the instantaneous rate of change of the f of x and the change of the slope of a tangent line are the same at the point of tangency. Now the last one is that the y value, the height of the derivative function, I wrote here the height of the derivative function for an input x. X is an arbitrarily is an arbitrarily element, which means if it is true for x, is true for every other point in that interval. So providing the slopes, what that provides, providing the slopes of the tangent line to the graph of the original function at x f of x, which means at the point in the graph of the original function. Okay, please pause, contemplate, think, reflect before you go to the next. So let me go now to the next, if I may. So I'm going to illustrate them also with the graphs and diagrams after I finish this one, if I may. Okay, now let me go over that one. For an input x, the y value of the derivative function provides us, it gives us the slope of the tangent line to the graph of the mother function f of x at this particular point, single point, geometrically. That is the geometrical interpretation. All right? Now, instantaneous rate of change of the f of x mother function at this point on its graph, that is analytically. So instantaneous rate, when we talk about, is analytical approach. A slope of a tangent line we are discussing is geometrical interpretation. Okay? Now, a slope we know is equal to rise over run. Is that right? And now I wrote delta y over delta x, but I put t here. That means delta y, the change of y of the tangent line. Not the graph of the mother graph, not f of x, but tangent line. So a slope times delta x equals to delta y of the tangent line. Do you follow me? Now, as delta x approaches 0, then s times dx We know what dx is, the limit of delta x as delta x approaches 0. The s times delta x will be dy, which means the limit of what? Of the rise. Now this is same as f prime of x, because when I give value to the derivative function, he gives me what? He gives me the slope of a tangent line. Geometrically, they will be the height of the derivative function will be the slope of the tangent line, geometrically. Now, if I multiply that one by dx, I will get what? I will get the change in my rise, dy. Do you follow me so far? Now, I'll say the word but f prime of x times dx is the product of two numbers, is that right? Like 2 times 3 I mentioned in the previous lectures, 2 times 3 can be interpreted in a 2D as the area of a rectangle 2 by 3 dimension. So f prime of x, which is a number, we give x, it gives you the value, times dx is what? Is the area of a very extremely thin rectangle. Now, the height of this rectangle is f prime of x, the output of the f prime of x. And the width of this rectangle is the dx, which is the limit of delta x as delta x approaches 0. So far so good, huh? Now, if we add all of this, which means all these rectangles, very thin rectangles, will be the area of what will be fill up. If we add all of them, will fill up the area under the graph of the derivative function. The graph of the derivative function. So please pause, think, reflect before you go to next. Okay. Now we go to illustration. Now let me go through the illustration for that. Now let me cover the bottom one first. Now here, this is the mother function, the dot, all right? And now this is the tangent line at this point that is a kind of, I selected x, as I say, x is an has arbitrary value. Therefore, this is the case for every single point in the given interval or the domain of the function. Of course, because we are talking about derivative, the function we are assuming to be differentiable to begin with. Now notice that as we go away from the point of tangency, the gap between the tangent line and the graph f of x increases. You notice that the gap is increasing. Now, as we approach toward the point of tangency, the gap decreases. At the point of tangency, the rate of change, analytical rate of change of the f of x, and the graph of the tangent line, a slope of that will be same. So they will have same rate of change at the point of tangents. Now, here is the same that I mentioned it in this one. Now here, I give a value to my derivative function. This is f prime of x. Let me, in fact, write it so that you can see. This is f prime of x. This is f prime of x. Now I put the linear, but we will come to kind of examples that this f prime of x may not be linear, but just for a beginning comprehension, we will be covering that in the coming future, in the coming lectures. Now, when I give a value to my derivative, when I give x, he gives me a value, is that right? Which is the height of f prime of x. Now, the height of this is the slope of a tangent line to the graph, that this is the derivative of that graph, at that x point. We don't know f of x, we know input of that. And as you see now, I select another x closer to the point of, another x to that, just for extra work, is that but when I give x, he give me a value, and the value of that will be a slope of a tangent line to the graph, mother graph, let's call it, at that input x. So this is another. Now let me go to next one. Again, please pause, think, reflect before you pass to the next. Okay, now let me go to the next one. Next one, I think I may need to zoom it because it's not vertical. Let me see if it is zoomed. Excuse me. Not bad, huh? Hopefully it's visible to you. Okay. Now is another illustration. This is the graph of derivative of function. All right. And now this is what we went over, in fact, in the previous lecture. Now this is when I give x, f prime of x, give me what, which is the height of that, give me the output. Now that output times dx, this tiny will be dx, will be what? Will be the area of this rectangle. Now this area of this rectangle, starting from the left end point of the interval and continuing all the way to the end of the interval, give me the area under this graph. Do you follow me? And the area on this graph ends up to be the mother function. So I will have more examples for that. I will be making more examples so that we become more explicit. Okay, the final one is something that we have seen it. It's just for extra repetition for you to think and reflect or keep repeating that because it's very important. And that it will be this. Now, the goal is to determine f of x knowing the derivative of x. So I went to the slope, which is rise over rho, delta y over delta x. And delta y over delta x, don't forget I did write tangent, which means we are talking about rise over rho of a tangent. And then as you notice, as we go away from the point of tangency, the gap between the tangent line and the original graph increases. And as we approach to the tangent point of tangency, that gap decreases. At the point of tangency, there is no more gap. You follow me? Okay, then let me pause that one. Let me say also a few words about something important just for the sake of it. That if you are stuck on a, say, hard problem that you do not have the faintest idea how to start, right? Try solving a smaller analogous example, and then the solution of this simpler version can serve as a prototype to help you tackle the original problem. I have mentioned that one in my strategy of problem solving in one of my videos, and I do encourage you to watch that one, and there are some good hints for them. Okay, then let me zoom this one back, say a few more words, and be close to this lecture. May I please? Okay, then I thank you for watching, as always, and I'm intending to put possibly entire calculus, if I get the opportunity, some selected topics, and hopefully I will have that opportunity to do that. And please, I keep repeating at the end of each lecture that if you have any comment, any suggestion, if you may notice any error, please do mention it in the comment section below, and you will be doing me a great favor. Okay, then for the second time, I thank you for watching. I wish you all prosperity and good health. Please stay and remain healthy. Salam.